This is not just any speed, but the precise minimum velocity an object needs to break free from the gravitational influence of a celestial body. Think of it as the cosmic speed limit, the one that governs the movement of everything from a rocket to a humble stone. Unleashing the secrets of escape velocity will let you grasp the intricate dynamics of our universe. Gravity, the unseen force, keeps us grounded and governs the movements of celestial bodies. This invisible power is responsible for a whole lot more than just keeping our feet firmly planted on the Earth. It's the engine that drives the orbits of planets, moons, and stars. It's the glue that holds galaxies together, and it's the force that shapes the universe itself. So how does gravity work? At its most basic, gravity is a force of attraction. Every object in the universe, no matter how small or large, exerts a gravitational pull on every other object. This force is proportional to the mass of the objects and inversely proportional to the square of the distance between them. In simpler terms, the heavier an object is, and the closer it is to another object, the stronger the gravitational pull. Our Earth, being a relatively large mass, has a substantial gravitational pull. It's this pull that keeps us, buildings, animals, and everything else from floating off into space. It's also this pull that keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. But gravity doesn't just hold things in place. It also affects the speed at which objects can leave the Earth. To overcome Earth's gravitational pull and venture into space, an object needs to reach a certain speed. This speed is known as the escape velocity. For Earth, the escape velocity is about 11 kilometers per second. That's approximately 33 times the speed of sound. It's the speed a rocket must reach to break free from Earth's gravitational pull and venture into outer space without continually expending fuel. It's important to note that escape velocity doesn't mean an object has to maintain that speed forever. Rather, it's the initial speed needed to break free from a celestial body's gravitational field, assuming there's no other force like air resistance or thrust from a rocket engine at play. Escape velocity, then, is a rebellion against this fundamental force. It's the speed at which an object says no to gravity and dares to venture where gravity no longer reigns supreme. Escape velocity isn't a random number. It's a fascinating calculation involving some basic principles of physics. Now let's delve into the nitty-gritty of how we calculate escape velocity. The formula is quite simple. The escape velocity equals the square root of 2 multiplied by the gravitational constant multiplied by the mass of the planet divided by the distance from the center of the planet to the point of departure. Let's unpack this a bit. The gravitational constant, represented by the letter G, is a key figure in physics. It's a really small number, about 6.674 times 10 to the negative 11th power. It's so small because gravity, although it's a force we feel every day, is actually the weakest of the 4 fundamental forces of nature. Next up is the mass of the planet, represented by m in our formula. This is pretty straightforward. For Earth, that mass is approximately 5.972 times 10 to the 24th kilograms. But if we were calculating the escape velocity for, say, Mars or Jupiter, we'd use their respective masses. Finally, we have r, which stands for the distance from the center of the planet to the point of departure. For an object leaving from the surface of the Earth, AR would be the radius of the Earth, about 6.371 million meters. So when you plug in all these values and do the math, you get the escape velocity. For Earth, that's approximately 11.2 kilometers per second. That's right, per second. That's over 40,000 kilometers per hour. It's a mind-boggling speed, isn't it? But remember, this is the minimum velocity an object needs to completely overcome Earth's gravitational pull without any additional propulsion. So, escape velocity is a precise calculation, showing us the power required to defy gravity. Understanding escape velocity is one thing, seeing it in action is another. Let's dive into some real-world examples of escape velocity and how it has propelled us into the vast expanses of space. Take, for instance, the Apollo moon missions. In order to break free from Earth's gravitational pull and journey to our lunar neighbor, the Apollo spacecraft needed to reach an escape velocity of nearly 25,000 miles per hour. That's about 33 times the speed of sound. This speed allowed the spacecraft to overcome Earth's gravity and set its course for the moon. Another fascinating example is the Voyager missions. Launched in the late 70s, both Voyager 1 and Voyager 2 reached escape velocity to not only leave Earth's gravitational influence, but also to exit the solar system entirely. These spacecraft are now in interstellar space, the region between stars, journeying farther than any human-made object has ever gone before. Then there's the New Horizons mission to Pluto and beyond. Launched in 2006, New Horizons achieved the highest launch speed of a human-made object from Earth. It reached escape velocity in just 9 minutes after launch, covering a distance of over 3 billion miles to reach Pluto, and continuing its journey into the Kuiper Belt. And let's not forget the Mars rovers. These robotic explorers had to reach escape velocity to leave Earth and travel to the Red Planet. Once there, they've provided invaluable data about our neighboring planet's geology and potential for past life. These are just a few examples of how escape velocity has been vital in our quest to explore the cosmos. From moon landings to interstellar journeys, the concept of escape velocity has enabled us to push the boundaries of human exploration and knowledge. These instances demonstrate the practical application of escape velocity in our exploration of the cosmos. What happens when an object achieves escape velocity and breaks free from Earth's gravitational pull? Well, the moment an object reaches escape velocity, it's like a bird breaking free from a cage, except this bird is soaring not just into the skies, but into the vast expanse of the universe. This object, whether it be a spacecraft or a probe, is no longer bound by Earth's gravitational field. It has the potential to venture out into the cosmos to explore and discover what lies beyond our home planet. Achieving escape velocity is not just a feat of engineering, but a testament to human curiosity and our enduring spirit of exploration. When we send a spacecraft hurtling into the cosmos at escape velocity, we're not just launching a piece of metal and circuitry, we're launching a part of ourselves, our hopes, our dreams, our insatiable quest for knowledge. So what does it mean to explore other planets and galaxies? It means that we have the capability to reach out and touch the stars, to gather data about distant celestial bodies, to look for signs of life elsewhere in the universe. It means that we can send rovers to Mars, probes to Jupiter, and even aim for the outer reaches of our solar system. Being able to achieve escape velocity has opened up a whole new frontier for us. It's like we've been given a key to a door that leads to an infinite hallway of possibilities. We can study asteroids and comets up close, examine the atmospheres of other planets, and delve deep into the mysteries of black holes. But it's not just about exploration and discovery. Achieving escape velocity has practical applications too. It's what allows us to place satellites in orbit, which in turn helps us with communication, weather forecasting, navigation, and a host of other things that we rely on in our day-to-day lives. In a nutshell, escape velocity is our passport to the universe. It's what propels us beyond the confines of our own planet and into the great unknown. It's what allows us to dream big, to reach for the stars, and to keep pushing the boundaries of what we know and what we can achieve. Escape velocity is our ticket to the vast expanses of the universe. So, we've journeyed through the concept of escape velocity, understanding its calculation, and its role in space exploration. We've delved into the gravitational pull, the mathematical equations that determine escape speed, and how this concept comes alive in space missions. Escape velocity, this crucial key in physics, not only propels spacecrafts beyond Earth's atmosphere, but also guides our understanding of the cosmos.